Is lung cancer rate correlated with smoking rate? This is a correlation, and this little exercise should help you do your homework this week. We're asking you to find the average deviation of a data set. So I'll find the average deviation of this data set. It's one we worked with in class, and I hope that makes it easier for you. So on the x-axis down here, we have smoking rate as a percent of the state population. There are 10 states represented in this survey, 10 points. Over here on the y-axis, we have the lung cancer rate measured as the number of people per thousand who get lung cancer. Step one was to install the best fit model, which we did with a line, and the idea here is to wiggle the line around until you minimize the variability, which means to shrink up the distance from the points to the line that you choose so that the distance is minimized. And something like that is pretty good. The human eye can do it pretty accurately. So let's go ahead and install that best fit model like this. We got it, and now let's determine the deviation from the model down to each point, or from the point up or down to the model. And you do it this way. Here's a point. We're going to draw a vertical line because the vertical line follows the y-axis. And what's this deviation? We got to go over to the y-axis to get it. So from about 50 to about 53, this deviation is 3 people per thousand away from the model. Let's go up here and do it for this one. This is about 60, and it goes down to about 55. 60 down to about 55, so we're going to estimate this deviation at 5 people per thousand. Over here we'll do it again. This is from about 55 up to about 58, so there's another deviation of 3 people per thousand. From about 68 down to about 60. I'm working quickly here. That's 8 people per thousand. So let's go ahead and do it for the rest of these points. We're finding the deviation for each. And you can do it this way too. So this deviation, I'm looking over to the y-axis, is about 5 people per thousand. This is pretty close to 0. It's right on the line, so we'll call it 0. This point is about 7 people per thousand away from the model. This point is about 4 people per thousand away. There's another, let's call it 0, pretty close to the line. And this deviation is another 3 people per thousand. So we measured all the deviations from the model. Now let's add them up, which I did, and it's 38. And 38 divided by the number of points that we have is 3.8. So it'd be 38 divided by 10 equals 3.8. So up here I'm going to write the average deviation is about 3.8 people per thousand. Now we can use that in the next step when we make a prediction. So here's a place in the data where we don't have a lot of data, from about 54 up to 58. So usually you can, if you have a model, you can go ahead and make a prediction where you don't have any data. So let's choose 55. There's 54%, 56%. Let's just say, what if we had a smoking rate of 55%? 55%. What would our model predict the lung cancer rate would be in that state? And the way we do it is to go from 55% up to the model, and then over to the y-axis to see what the prediction would be. And that looks like about 79 people per thousand. The model predicts it for a smoking rate of 55%. You get a lung cancer rate of about 79 people out of every 1,000 who get lung cancer. And then we ask ourselves, okay, really exactly 79? Can we say that with confidence? No, but we can give a range. And if the average distance from this best fit model is 3.8 people per thousand, that means that the actual number, let's call this 4 just to make the math easier. This actual number could be as easily 79 as it could be 4 more of 79. So 83, 79 plus 4 gives us 83. Or it could easily be 4 people per thousand fewer than that. So 79 minus 4 gets us down to 75. So now what we'd say is that for a smoking rate of 55%, we can be pretty sure that according to this model, built with these data, the lung cancer rate would be somewhere between 55 and 83%. So that's how you do your homework. Good luck. Come in and get help.